Uh, Hello, everyone. Welcome back. All right, so now we have the first keynote session for ATVA 2021. Our first keynote speaker is supposed to be Sir Tony Hall, but unfortunately, Tony has been ill recently, and his current condition doesn't allow him to do the presentation live today. So he's been resting at home. I wish him a speedy recovery. Nonetheless, I've been very lucky to have worked with Tony and Professor Bernhard Müller on this deck of slides. And they both wanted me to deliver the keynote on behalf of Tony today. So I'll begin with a short introduction, which may not be necessary as I'm pretty sure everybody knows who Tony is. But anyway, so Tony Hall is a British computer scientist. He developed the sorting algorithm quicksort in 1959. He also developed Hoare logic, which is very famous and is used for verifying program correctness in 1969. He also developed the formal language communicating sequential processes, short as CSP, to specify interactions of concurrent processes, and that was developed in 1985. He received the Turing Award and Kyoto Prize for his fundamental contributions to the definition and design of programming languages. Tony Hall became a professor at Oxford University in 1977, where he's now an emeritus professor, and was elected as a Fellow of the Royal Society, as well as a Fellow of the Royal Academy of Engineering in the UK. A recent personal research goal of Tony has been the unification of a diverse range of theories applying to different programming languages, paradigms, and implementation technologies. So today's talk is a part of a series that explores the relationship between programming languages and geometry. Before Tony was ill, he did a recording session with me in which he gave the opening of the keynote. So what I'll do is I'll just play the opening of the keynote recorded by Tony, and I will take over from there. It's a very short video, about 5 minutes. Sorry, I just need to carefully change this resolution. Otherwise, YouTube would be changing it automatically every minute.
A geometric theory for program testing. Thank you for this valued opportunity to address your virtual conference, ATVA 2021. I will present a simple theory of finite geometry, which has been developed by Bernhard Müller and myself to assist in the laborious process of program testing and debugging. The lecture starts by describing the design of a graphical environment for inclusion as the last component of a tool chain of an integrated software development environment, abbreviated to ISDE. Earlier versions of a partialized ISDE are already delivering benefits in the software industry. They reduce the lifetime costs of development of commercial software products, particularly on the longest and last phase of a software evolution, more than 20 years. Well, very often. My description of the design will exploit and develop your geometric intuition about the behavior of a program when it is executed. My ambition is that this will similarly develop the intuition of students seeking a degree of Master of Software Engineering Without a professional education, few programmers will be found for any new industrial ISDE, even if it were available now. On entrance to the master's degree, the entrant should recall with pleasure the mathematical topics at high school, particularly geometry, algebra, and logic. They should have an acquaintance with a programming language, preferably a sequential or functional style language, and they should be keen to discover and exploit new features, concurrency and object orientation. The material of this lecture should be taught as part of the first compulsory practical programming module of the degree, CS 101 perhaps. It's cruel to teach students to write a program without telling them effective methods to test it. Even professional programmers spend more than half their time testing their programs. The professional course should start, as I said, in CS 101, together with the compulsory practical programming module. This will develop the beginner's essential skills in program testing. Later modules will introduce a range of important computer applications, like spreadsheets, database support, web page design. Each module will introduce a widely used special purpose language for programming that particular application. These special purpose languages are now widely implemented in commodity apps, for example, spreadsheet services and database searches, or in the hardware of GPUs and FPGAs. Educational versions of these tools will share the same ISDE as in CS 101. Our treatment of geometry owes everything to the ideas and inspiration of the pioneers of the subject. Euclid defined the basic concepts of plane geometry. We will exploit his treatment of points, lines, figures, and their edges. We will exploit his famous parallel postulate. 2,000 years later, Descartes introduced orthogonal axes and coordinates. He required that the point is a unique element at the intersection of a pair of orthogonal coordinates. Although I shall ignore those features that I do not need in my treatment of the past teachings of these pioneers, for example, I will not require that every such intersection of coordinates should contain a point at all. In practice, most of them won't.
Okay, so that was a short opening recorded by Tony. Now back to me, and I'll continue to finish this keynote. So just now, Tony talked about some pioneers in ancient history, but in modern times, the US linguistic Noam Chomsky introduced syntax trees to define the grammar of sentences of a natural language. And these are now also widely used in defining syntax-free features of artificial languages. So in such a definition, a tree is defined to be either a root or a subtree, which would involve a branch or a leaf as shown by the labels. And we will only need binary trees in our work, which are a simple, useful simplification of our diagrams. Now, another pioneer is the German mathematician and computer scientist Carl Adam Petri. And he introduced, back then it was called pastry nuts, now it's called Petri nuts. It's dynamic logs and traces of the behavior of a computer in a single execution of a single program. A history net consists of interconnected transitions, and each of these has a certain number of input and output arrows, which may carry a single pebble or noun. So in this talk, I may use the word pebble, whereas in PetriNet, in the literature, it's usually called tokens. A transition can fire if and only if all its input arrows carry pebbles. And the pebbles flow through the transitions from the top to the bottom, like what's shown in the animation. Okay, so that's a very simple example and animation of the firing of PetriNet transitions. Select the illustrations of the previous slide. Our directed graphs are diagrams which can be drawn on a conventional sheet of graph paper. The nodes record events occurring in or in a peripheral device of a computer that is executing or has executed a program under test. The arrows represent a causal dependency relation that prevents the event at its head from occurring before the event at its tail. Therefore, the occurrence of the head event causally depends on the prior or simultaneous occurrence of the tail event. Hence, the causation is an enabling condition that is necessary, but is not sufficient. For each event that occurs, it is necessary that all its enabling conditions have occurred, either earlier or simultaneously. Now, as on the conventional graph paper, there are two axes. The horizontal is for space and the vertical is for time. And in our presentation, the space coordinate points to the right and the time coordinate points downwards. So here's a diagram of the points at a collection of all those points principally available on a sheet of a graph paper. And those points, they represent all the events occurring in an execution of a single node in the syntax diagram of the program. In one of the earlier versions of this work, all the lines that we are drawn as arrows. And now to reduce clutter, we remove the arrowheads and only draw the lines. Okay? But we may still use the words arrow and line interchangeably throughout this talk. For instance, in this slide, we show 7 blue vertical lines. You can also call them vertical arrows. So those arrows will be pointing downwards. And they are mutually parallel in the Euclidean sense that they do not share any points. Each of them records the complete history of the action of a single separate object in computer memory. For example, each line may represent a resource, a variable, a channel, or a thread of a concurrent program. And the points that lie on each coordinate represent the successive observations performed by or on that object. So implicitly, all the blue arrows point downwards, and all the horizontal arrows will be pointing to the right, which we will show in later slides. The local coordinates of a slice are those that do not pass through any of the surrounding edges of the slice. So you can see them in the middle of this diagram. Now, the earliest point of such a coordinate, so this one, the earliest one, would represent the allocation of a resource, and the bottom coordinate is its disposal. Okay. So this remark gives an intuitive definition of the purpose and meaning of allocation and deletion, but it gives no hint of how the purpose may be achieved at runtime or in a stack or on a heap, nor does it determine where or when each event occurs. So these are all decided by the implementation of the language, usually at runtime. There are 5 other vertical lines that extend through the edges of the slice. So they go beyond the slice, both above and below. And these are global resources owned throughout this execution. And this shows that the horizontal coordinates continue into the neighborhood on the left and above and reach the horizontally neighboring slice. And the vertical coordinates do the same for the neighborhoods above and below. Now we have 2 new lines. So these 2 new red lines at the edges of this diagram, they are synchronized communications inputting into the diagram on the left and outputting to the right. And there's a new blue line in the middle, horizontal line, and it represents a transfer of ownership from one thread to another. Right? And since it's horizontal, it shows that the release and acquisition of a resource are synchronized events. Now we have more horizontal red lines. So a horizontal line drawn in red records the virtually simultaneous execution of points lying on it. So these multiple points, so for instance, this one and that one, they may be terminal symbols of a grammar corresponding to basic commands, or they may be function calls. There's a function calls to class declarations at the lower level of abstraction. The points on each horizontal coordinate represent the simultaneous performance of events by 2 or more objects. And it must include a thread that issued the command. And it must be an action of an object that is currently owned by that thread. So there's a sense of ownership. The coordinate satisfies the classical definition of an atomic action, namely that there does not exist any instant in time at which some of its actions have already occurred and others have not. Now, again, the method of implementation and program execution is not mentioned in our model so far, but we'll discuss one example of how to execute that in the next slide. The alternative names in the title of the slide describe the various roles that the horizontal coordinate plays in potential applications. For example, they can be commercial transactions in blockchains, or they can be fences in a relaxed memory model. Now, as an example, this little section describes what Petri used for implementation. It's one of the examples of how to implement the program execution. We will visualize the firing of Petri nets in our familiar format of diagrams, and we will use the word pebble to mean tokens, like I said before. The arrows going into the box from the top and from the left. So these guys, those 4 arrows, they are input planes. And the arrows going out of the box to the right and to the bottom, they are output places. Each dot in the box, so we have 3 dots. Each of those dots represents a transition. Okay, so it's a slightly different visualization than the usual Petri net that you see. It's basically an analogy that we take that is adopted into our format. In the initial state, the diagram is dormant because it has no pebbles. It's no token. So here, the first pebble arrives on an input position, but no internal transitions can fire. Okay, because for the, let's say for the top left transition to fire, it would require a pebble at each of its input places. Now a second input arrives, but again, no transitions can fire. So here's the third one, still no action. But if the third one arrived on the red line above, then it would have fired the first transition here. Okay. But now we have the fourth pebble, and that activates all the three internal transitions. And the transition fires as the animation below. And now at this point, all the output lines are occupied, and no more input pebbles can be accepted until all the output pebbles have been consumed by the neighboring transitions. And this slice of PictureNet can never be repeated because it describes only a single execution of the program. We have just now described the order of execution of events of a slice, but we have not given any meaning to the internal components of the program. Now for this, we attach symbolic names to the components, coordinates, and basic commands. Each name is one that appeared originally in the source program that we want to model. And this is essential in program testing to understand where and how the program should be corrected. The purpose of label is to correlate the diagram and the corresponding program text. Right? So we have potentially labels on vertical coordinates, and those are usually object names. And on horizontal coordinates, those are usually basic commands or function calls. Each arrow may also be labeled by a relevant value, and that would be useful if we want to see the state change of those variables. Now this diagram on the right-hand side has dotted left vertical lines, has a dotted left dotted line. And it indicates that the left part of this diagram has been omitted for clarity, but we will show them on the later slide. The input and output interface coordinates, those are labeled by unique names or addresses of those objects. Now each name belongs implicitly to some object class. For example, here we have an output thread, and the output thread is denoted by an exclamation mark. Okay, we also have a variable y. And we have an output channel. It has a subscript 37. So that means it communicates the 37th message on the channel D. The class defines and determines the correct behavior of all its objects. Now this diagram of the left part of the slice has two threads named T and U. There's two threads. We have a variable named X, and it's an integer variable allocated and disposed locally to this diagram. It is represented by the location number, or i.e. reference of the object in the memory of the computer. The label C exclamation mark denotes an input port of a communication channel C. Now again, the subscript 84 means it is the 84th message communicated on this channel. Now, this diagram has been obtained by joining the two previous diagrams at their dotted edges and then removing the dotted edge. Because now we have a combined diagram that gives you the whole picture of a very small program. Now we can put more things on the horizontal coordinates. So in this diagram, each horizontal coordinate is labeled by the basic command in the thread, which has triggered the execution of the atomic event. For example, on the left-hand side, look at the left-hand side, the actions of the thread T. So we have three actions. So they are an allocation of the new object X, an input of the message on channel C, simultaneously, so that's the input, simultaneously with the assignment of X. And the third one is a release of the ownership of X. Now we look at the right-hand side of the diagram. So those are mainly about the actions of the thread U. Okay. So we have an incrementation of the variable Y. We have an acquisition of the ownership of X, an output on channel D, and disposal of the object X. Right? And the indices on the release and acquisition, so in the middle of the diagram. So those are the serial numbers of those actions in the life of the variable X. Now we can add even more things to the diagram. So on this slide, the additional both numeric labels on each arrow indicate the value transmitted from the tail to the head of the arrow for the performance of those actions. On the vertical arrow, let's say this one, the label is the current value of the object during the interval between the occurrence of the tail, which is right here, and the head. Okay, on the horizontal coordinate arrow, let's say this one, the incrementation, the y equals y plus 1. It is the value of the message communicated. The correctness of values may be easily checked against the rules that define each expression or basic command in the language. The state of executing computer memory at the beginning of execution of a slice and at the end is defined as the function that maps the name of each arrow crossing the top or bottom edge to the value which labels the arrow. And so implicitly, we have a partial function that represents the memory. For example, at the top edge of this diagram, looking at the top edge, the initial state maps the variable y to the value 3, whereas the bottom edge gives you the final state that maps the variable y to the value 4. Now, a similar function describes all the interactions between neighboring slices that occurred during execution. For instance, if we look outside of the current slice, we know that C84 has the value 8. Our model of program execution so far has been entirely event-based. It's an event-based model. And we have just explained how memory can be introduced into an event-based model. is defining chains of events by exploiting the labels for objects and values that are attached to the vertical coordinates. Now, putting things together, so let's recap and have a look at the whole story of this part of execution of, I'd say, it's an extremely unlikely segment of a program. So the story starts the left part of the slice with an allocation of new object X by the thread T. This is followed by input of the initial value 8 from the channel. And this is simultaneously assigned to the variable X. Then the thread T releases the ownership of X, and the other thread U simultaneously acquires the ownership. Meanwhile, on the right side of the diagram, so the thread U has incremented the value of its own local variable Y. It then acquires X from the thread T and outputs on its output channel the sum of X and Y. And finally, it disposes the object X. Okay. So when we read a diagram like this, we read from the top left corner to the bottom right corner. And this whole diagram tells you exactly the same story as the text on this slide. Right, so this slide, in this slide, we use the usual semicolon in a familiar way to denote sequential composition, which is, as done by every programming language. And we use a single vertical bar to denote concurrent composition. Now, this is done as in process algebras like communicating sequential processes. So, in fact, it is a great simplification to treat concurrent compositions as a simple binary program connected, just like the semicolon, which calls for sequential execution. And their properties, like transitivity, can be expressed axiomatically. And the program can be transformed for purposes of compilation and optimization. We're now ready to add more program operators to our diagram. So we talked about sequential and concurrent composition in the text. So in this section, we're going to add those things in our diagram. The definitions of those kind of program composition operators usually follow the normal style of definitions in the natural science and in applied mathematics. Each technical term is defined by relating it to the real-world phenomena which it denotes. This often describes in general terms the purpose and the intended effect of the defined concept without giving even a hint of how it is implemented. For instance, this slide shows a vertical slicing, okay, so in the middle of the diagram, by introducing an internal vertical edge in the slice. The title at the top of the slide gives you the concrete syntax of the program that was executed. Okay, so P parallel Q. The vertical bar symbol indicates concurrent composition of these two operands. And the new splitting edge in the diagram, together with all these arrows that go across it, is shared between the two component boxes. So now we have a left box and we have a right box. It appears, so the edge appears on the right vertical edge of P And there's a left vertical edge of Q, and they are indeed the same edge. Okay, same edge splits the boxes. The horizontal coordinates are also split into two disjoint line slices. So we have a line here, and we have a longer line on the right-hand side. And they're split at this point introduced by the edge. And then it is immediately obvious from the horizontal edge at the top of the diagram that the two components P and Q, they start together same time, and they also finish together. Okay, it's a very intuitive presentation as required by the definition and purpose of concurrent composition. And furthermore, the top edge of P is wholly disjoint from the top edge of Q, and consequently the vertical coordinates that cross the top edge of P, so these two blue lines, they are wholly disjoint from those that cross the top edge of Q. And same is true for the bottom edges. And this disjointness is very important. So this disjointness is the intuition behind Peter O'Hearn's separation logic. It's a disjoint of resources. And the local variables of a slice, so for instance, that was the X in the previous example. So those local variables are called the footprint. An ownership discipline for threads and objects is designed to prevent a risk condition between two threads for accessing the same object. And such a race is a source of uncontrollable non-determinism, which we don't want. And we have already prohibited races by the rule that every vertical edge between two threads must pass through a vertical blue arrow. The synchronization of the transmission of ownership is generally more efficient than the synchronization for vertical coordinates, horizontal coordinates. And like sequential composition, this kind of transmission usually has no runtime overhead. The semicolon denoting sequential composition is represented geographically by a horizontal split in the diagram. The state of the memory of the executing machine passed from P to Q is defined by the edge that they share. Okay, so this horizontal edge would give you the state of the memory going from P to Q. Note that it is geometrically impossible for any arrow to point upwards, because we have the assumption that the vertical coordinates always point downwards, so you can't go back in time. So you cannot have any arrow that goes from Q to P. Such a crossing, if such a crossing were possible, then the principle of causation would require the implementation of to start executing the component Q before finishing the execution of P. And this is ruled out by the definition of semicolon together with the definition of causation. In Euclidean plane geometry, it is also impossible for a horizontal arrow to cross horizontal coordinates. Okay, so they are parallel. And this is intended to denote, those red lines are intended to denote atomic events. As the memory can never be in a state where some of the actions on the coordinate have already happened and some of them have not. It is prohibited as our definition of parallelism by Euclid's famous but controversial parallel postulate that forbids it. This slide illustrates how diagrams formed by previous splits can be splitted again. The bracketed operator of the program those bracket operators, gives the orientation or precedence of the first split. Subsequent splits on the internal slices may be either parallel or orthogonal to it. The process of splitting can be continued until all the diagrams contain only a single horizontal point, which would mean that every slice would be an atomic event. This is how the previous diagram is distinguishable from the current one, in which the first split is horizontal and the second and third splits are vertical. Okay. So just now we have two things executing in parallel. Now we have two things executing sequentially. But if you take a close look at these two diagrams, although they have different ways to split the diagram, they actually represent this. They will give you the same execution of the program. And this is a visualized view of the interchange law in separation logic. In summary, we have illustrated the geometric constructions by application to an example program execution, which includes many of the essential features of C++ and other modern object-oriented languages. So those features we have considered in the example are listed on this slide, and they include features that have been omitted from most of the other formalisms of programming language designs. Okay, so we have included variables, channels, threads, and other resources. We have transactions. We have allocation and disposal of some resource. We have synchronous channels. We have assignments that updates variables. We have communications through input and output. And we have sequential and concurrent composition. But at the same time, we omit some features that are common to nearly all such formalisms in our example. For instance, we don't have types. We haven't considered conditionals. We haven't considered loops, timing, or weighting, or probabilities. And so those can be added in future work. Now, in the elements of Euclid, geometric diagrams are good for conveying ideas and intuitions. And the only formal text material in the diagrams will be the labels that name the components of the diagram. And they are the same names used in Euclid's proofs and in our programs. This keynote is a part of a series of related lectures, monographs, and summer schools listed on this slide. So in the series, we have algebraic theory for program design, which is a keynote that Tony gave at SCFEM 2018 on the Gold Coast. The second one is predicate calculus for program specification, which is essentially whole logic, and nowadays may be extended with separation logic. Third one is quantum theory for quantum programming and machine learning. And the fourth one is navigation tools for error detection and repair. Related to all those lectures and keynotes, there's the Verified Software Initiative, which was started as a wide international collaboration in 2005. And its second of 3 phases will build on its achievements in the construction of theories, tools, and experiments. And anyone of this audience will be welcomed to join. And let's conclude with a discussion on program testing. The purpose of testing, we summarized 3 of them. So first one is to locate errors, particularly for those errors that are in the interfaces between large components and those are in recently changed code. So those are the places where people frequently make errors. The second one is to assist in the diagnosis, search for a correction or an acceptable workaround. And lastly, we want to record the evidence for code reviews and analysis. Any realistic theory for program testing should be based on a study of the different kinds of errors that may be detected in the execution of an arbitrary program. And these may be classified in two ways. First are those errors in the program under test which the programmer is capable of fixing. The second are those errors that require fixing by someone else. This slide gives some errors that can only be due to the fault in the implementation itself. The first 2 points violate rules which we have quoted as part of the very definition of the programming language. And the first one, we can't have any arrow or line that goes from Q to P in P sequential Q. Right? And we've talked about that in sequential composition, so you cannot go back in time. So in the visualized view of a program, if you have a vertical arrow that crosses if you have a horizontal arrow that crosses a vertical coordinate, that would obviously be an error. And other errors would include a failure to detect falsity of an assumption, which is a precondition made by the assumed by the programmer. And there could also be errors that have prevented the execution. So there could be some syntactic error, which would stop the compilation. There could be some type mismatch and other things. So I may just add one more thing on the second dot point, in case you're wondering. So if you have a horizontal arrow that goes across vertical coordinates, let's go back to one of the examples. So those are the vertical coordinates. Right? So the only horizontal lines that can go across those vertical coordinates are the input and output of the program. So if you have any red lines, which are what we call the horizontal arrows. If you have any red lines that go across the boundary of the slice, that would mean there's some resource that is supposedly local in your program, but it is used outside the scope of the program. Okay, could be a Stack Overflow. What? Now this slide describes generic programming errors that are explicitly ascribed to the program itself. And they are the errors that program testing is aimed at detecting. So for instance, we're looking at non-termination, including deadlock. We're looking at vertical split, crossing a red horizontal arrow. So we talked about vertical splits. They should only cross a blue horizontal arrow. They should never cross a red horizontal arrow. Okay, so a red horizontal arrow would represent an atomic action. And if you have a vertical split, then you may have the issue of executing parts of that atomic action before the other part. Other errors include an operation that is explicitly forbidden by the language. For instance, it could be zero division, could be null the reference, or some assertions that are evaluated to false, which violates a promise made by the programmer. This slide illustrates the ease of introducing new operators into our geometric model of program execution by simply placing different restrictions on the kinds of errors that cross between these operands. So in this slide, the first definition has three vertical bars, and it is most restrictive operation, meaning interleaving in CSP or in or sometimes it's called separating conjunction. The second one with the double greater than sign is the least restrictive, and it means chaining or piping Unix. And these two definitions also drew out deadlock. Now, so much for the theories, but in an ideal world, we would like to see some theories being implemented in user-friendly interfaces. Okay, so we would like the tool to be able to select and generate a suite of test cases that exercise recently changed code. We would like to locate all such violations in the resulting trace and potentially mark those responsible commands so it's easier for the program to find. We would like to present navigable display of the trace following that allows travel along the causal chain in either direction. It'd be nice if we can zoom on multiple selected regions of a diagram, and could be a lot of other things we can do with the user-friendly graphical user interface. This is the last slide. So Tony had 3 questions to the audience. First one is, could the diagrams help teach concurrent program object-oriented programming in CS 101? Could a display of diagrams assist in student program debugging and in their assessment of progress? Could the diagrams enliven a course on theory of programming? So those are some of the long-term questions. And if you have any questions, you can ask me. I'll try my best to answer. If I cannot, then I'll relate that question to Tony. And Tony would be more than happy to receive a ton of questions from you guys. And he would like to have some email exchanges and technical discussions with you. Thank you all very much. Questions? Has this been implemented or prototyped in any ISDE yet? My answer would be no. So these are all only conceptual development. And yeah, that's what Tony does these days mostly. So he likes to develop these kind of concepts and then leave the actual implementation to other people, which is part of the reason why he encouraged people to join the Verified Software Initiative. Let me go back to one of the previous slides, this one. So part of that Verified Software Initiative is supposed to implement and realize some of the ideas that Tony has envisioned. But thank you, it's a very good question. Anyone else?
Okay, maybe a quick question. Can you hear me? Yeah.
Yeah.
Okay. Most of the diagrams always suffer this scalability problem when system getting very complicated. The diagrams, it's just not easy to compose, and so any comments on scalability of the approach?
Yeah, so I think I'm analyzing and modeling programs in these kind of diagrams. certainly, it may be impacted by scalability. And I guess at one point we have to think about how we abstract things at different levels. So for instance, each diagram may represent, let's say, some diagram like this may represent a function. And then on the red lines, you can write not only assignments but also function calls. So that, in a sense, would abstract parts of a big diagram into a small part. And which is why when we want to have this kind of zoom in and zoom out operations in the diagrams, if we want to do some visualized debugging.
All right. Okay. Thanks.
I also saw some other questions from the chat. So Mark asked, is there a URL for this initiative? Yes, I believe there is. Okay, I may need to do some Googling because I've seen it. So Tony has sent me that link before, and I will paste that in the chat in a minute after I get that from Google. The second one is, it would be interesting, so it was by Bernhard. Would be interesting to point out the relations and differences to message sequence charts and the variants. Right, yeah. Okay, that's a very good comment. I believe in one of the earlier versions of the slides, we did have the message sequence charts, but due to time management issues, we have omitted that. But yeah, so it would be good to have it, definitely.
Yeah, I think it's a good question from Bernhard. I think particularly the variant there, there's David Harrow has this live sequence charts. Something can maybe also quite relevant.
Yeah. Any other questions? If not, then thank you all very much for attending the session. I'm sorry that Tony cannot attend. I hope I did an okay job. And I think all the sessions will be recorded, and we're planning to upload that somewhere, probably on YouTube. And then after the conference is concluded, I will have a link on the website so everybody can see it.